Good evening, everyone. So I'm Prableen, and let's proceed with the week 5 of today's session. Let me share the screen. So let's start. Is it recording? Yeah, recording has started. So let us, where we have ended is, I have explained you what is MDP, Markov decision process. I have explained you an example of a robot where we have taken the states, where we have taken the actions, what are the rewards, that all I have explained you. Now, how are we going to proceed is, I'm going to take we have taken this robot example in the last class. I've explained you what is MDP. Now, what is the next thing? We are going to proceed with the value functions. So what is the value function, first of all? Value function is value for V pi is equal to expectation of GT given ST is equal to S. What is GT? What is ST? What does it mean? Am I audible first? Okay, let's proceed. So what is GT? GT is the return, expected return. If I am given with the state ST is equal to S, what will be the expected return? What will be the expected GT? That stands for V pi. According to policy pi, if we are in the state S, then what will be the GT, expected return here? Coming to the definition of Q pi, I'll explain you the difference between V pi and Q pi in a minute only. What is Q pi? It is what is the expected return if we are given with the state and we are given with the action. With these two equations, can you tell me the difference between V pi and Q pi? Yes. Am I audible?
Yes, I can hear you.
Can you tell me the difference between V pi and Q pi with these two equations?
Basically, for value function, we are just considering state, but not the action. In Q function, we are getting payoff. Means for a particular state, there might be the distribution of multiple actions. So we can pick up any actions, and against that, how much payoff we are getting.
Yes, you are correct. I can show you like this also. If I'm in a particular state, I'm going in the action, then S dash, then A dash, then S double dash. Or if I'm in the state, S1, A1, S1 dash, A1 dash, S1 double dash. Basically, if I'm in the state, then I am calculating what is the expected reward. This is V. What is Q is, I am in the state, I am telling that this action has to be performed here. Then what will be the expected payoff? Then what will be A1 dash? I am in this particular state, I am saying A is performed. A is already performed. Then what is the expected return here? As you said, here S and A both are given, and here we are given with the S only. Talking about today's plan, so I'll explain you this value functions, value iteration, and then I'll also give you some numerical examples so that we can get more intuition about this MDP. V pi is equal to expectation of GT. We can write GT as this is the expected return only. And as we know that expected return, we can write it in the form of the rewards, the discounted reward. It is the expected reward only. So we can write it in this form. Just I have elaborated this GT term only in this V pi. Now what I have done here is, this is RT plus 1 plus gamma RT plus 1 plus gamma square RT plus 3 and so on. What I have done here, just I have taken this RT plus 1, and this itself, if I'll have this gamma here, gamma, what is it? Again, RT plus 2 plus gamma RT plus 3. And again, I have basically written it as V pi of S dash. S dash means that now I'm going from S to S dash. S is the state I'm going, S dash is the state I'm going from S basically. So I have just written RT plus 1 plus gamma V pi of S dash to these terms basically. Bellman equation of V pi now. I'll write and then I'll explain you about this. Any idea about what is this Bellman equation? First, I'll ask you. Let's make this session an interactive one. Yes? Okay. Let's go step by step. I means policy. When I am in the state S, what is the policy tells me what action to be taken when I am in the state S. Now, I know what is the state, what is the action by the policy. What is the probability that I land into S dash? I was in the state S. What is the policy that through the policy I'll get what is A? Pi of A given S. Summation of S. Summation is basically I'm summing it over all A's here. and summing it over all S dash here. Then I am telling, I know S, I know A, probability of S dash given S and A. Here I got A. Now what is the probability that I know S and I know A? Then I land it up in S dash. Now I know S, A and S dash from here. Then what is the expected reward? What I am doing is, in the upper equation, I have written RT plus 1 plus gamma V pi of A. Wait a second, I'm sorry for the interruption. RT plus 1 plus gamma V pi of S dash. So RT plus 1, where was I? Plus gamma V pi of S dash. So RT plus 1, I have written it. What is the expected reward? If I know the action, I know the S dash. How do I know the action? By the policy. If I am in the state S, then what is the action this policy will tell me? And what is the probability if I know S, if I know A, I'll land up in S dash. Now, what is the expected reward? Plus this future reward. Clear? Or any doubt, I can explain you again.
Just the portion of just expected reward means what we are calculating is A S dash, and what is then this portion, this V pi of S dash in by into gamma, right? Multiplied by gamma, right?
Yes. If we'll go above, this is just an immediate reward I'm getting, RT plus 1. I'll go here. V pi is equal to expected RT plus expectation of RT plus 1 plus gamma RT plus 2 and so on. This RT plus 1 I have written here, okay? And this all I have written, this is the immediate reward I'm getting. This is what is the future reward I'll get. Gamma into V pi of S. You got it? How we get gamma into V pi of S dash here? Or
Yes.
So this is what I'm writing here, gamma V pi of S dash. This is same.
Yes, got it. No.
And this RT plus 1, I have basically split it into this.
Yes.
Now let's move forward. So what is here? Like once I know the S dash, I'll know about the expected reward, what will be it. And this is the future reward, return basically. So we'll study more about how the system is unique, how P is stochastic and all, like in just a moment. So let me first, this is the Bellman equation for V pi. Now the Bellman equation for Q pi. I'll write it and then I'll explain it. I'll write two equations and then explain together. Now, what is the first equation? We have studied this Q pi is equal to expectation of GT given ST and AT. Now, what is this? If we'll compare with this is the same equation I have written, just I haven't written this. I haven't written this basically, this policy. Any idea why? Okay. For the first one, this is for the like immediate reward RT. This is for RT plus 1, I am saying. RT plus 1, here I am saying we know the action. Here we know the AT is equal to A for Q. Here we don't know for the value function, we don't know what is the action. So that is why from the policy we said that A is the action. Here we know this A. So that is why I'm not writing this pi here. Got it? Or I'll explain.
Yes, I got it.
Now, this is the same. Now I have splitted this equation again to this. This is the same, this is the same. Now gamma v pi of s dash. Gamma v pi of s dash I have written as pi a s dash, pi a given s dash, q pi of s dash and a dash. Wait a second. Again, I have basically splitted this v pi of s dash into this form. What is v pi of s dash? Okay. I'll explain you in more detail. First, I'll go to this and then I'll explain. You got this equation, or I should explain? Like any idea? I'll explain it. Any idea what is this?
That is actually defining the value function under a particular policy. That I understand now. Q, this summation of this, if you can explain, it's better.
Yes. Now we'll again go. What is Q pi? It is expectation of return given ST and A. What is V pi? Again, I'm explaining expectation of the return only given that S. Now, what is it? The Q pi of S given A means Q pi, this Q pi is given to us. Wait a second, I think it should be Q pi AS. This Q pi is given to us. Now, if this Q pi is given to us, this is given to us. What is not given to us? That is this action here. If we'll compare this V pi and Q pi, here what is not given to us? This action. The same thing here. V pi of S is equal to Q pi of A or AS into policy pi S given A given S. If I'll explain it. If I'll write this Q pi of A of S, I'll write here. What does this mean? That expectation GT and S is also given to me and A is also given to me. If I'll write V pi of S, which means expectation pi, only S is given to me. So now, only S is given to us in V pi. V pi, only S is given to us. If we'll multiply with this, if A is also given to us in here, then we can say this equation. This is what this equation says. That if S, A given S, if we'll get to know about the policy and multiplied with Q pi of A of S, then we'll get V pi of S only.
Yes.
You got it?
Got it.
So that is what I have written here. In the place of V pi of S, I have written again this same thing, which I have explained here, this one. This is my now Bellman equation for Q pi. This is my Bellman equation for V pi. Proceeding further. Optimal value functions. Now what we want the maximum policy here. I can say maximum value here, basically. Maximum value function, which means Maximum return here, if I'm given expected return here, if I'm given the S for all S, or I can say maximum value function for every state. This is our main motive. You know about the policy. What is policy basically? Or you have any confusion in that?
No, policy, I understand that. That is the basically some sort of decision to take some actions, means for a particular, in a particular situation, means how will you go, means it might be deterministic or the stochastics, but there should be some planning like that, isn't it? Am I wrong? Hello. Hello.
Am I audible?
Yes, yes. Now you are audible.
Okay.
You were asking what policies, and I replied that it is a set of actions, means decided by the agent in a particular state. It might be deterministic or might be stochastic.
Yes. What do you mean by stochastic?
Stochastics means when we are not only exploiting, we are exploring something new, and we have some probabilistic value for, means every actions or our.
Can I say it is the stochastic means random here?
It basically, when it is chosen, I knew that it is chosen uniformly. Otherwise, every means options may not be explored or may not be taken care of. So that's why it is done uniformly, isn't it? Am I wrong?
Yes, it cannot. It can also be the case. Okay, you are saying uniformly. You are talking about the epsilon greedy thing.
Mm-hmm.
Am I correct?
Yes.
Okay, okay. So I want to discuss more about epsilon greedy. I should proceed here. Like, I want to clear your doubt. You said na uniformly. What do you mean by epsilon greedy first? Greedy means I'm only exploiting here. Like I'm only going to one state here. I'm like not going to other states basically. Other arms basically, sorry, state. In map, we don't have states or other actions basically. In epsilon greedy, we are also going to the other actions as well by a point, like we are also giving the equal probability so that we can explore the other actions as you told me. Am I correct? Now, there is also a limitation in this thing also. You know about that limitation?
No.
Okay. Like, suppose, okay, I have A arm, B arm, and C arm. And maybe I am having the material also. I can show you. This is the material. This is the Stanford. If you'll search about Stanford Thompson sampling, you'll get this PDF. This is very useful. You can also go through this. Here you will find, I think the next one, this is, here there is written, here only I have explained. Okay. Wait a second, I'll find that dithering concept. Okay, I'll tell you like this only. First of all, in greedy, what is it like? I have a 0.6. I got arm 1, arm 2, and arm 3. I'm having 3 arms. I have a 0.6 probability that I'll pick this arm. 0.6 probability that I'll get the reward 1. 0.4, I'll get the reward 1. 0.9, I get the reward 1, which is unknown to us. Is this the criteria? So basically, our main motive is we don't know about these probabilities and we want to know which is the optimal arm. This is the mapping. Now, suppose you get, okay, leave this. You get 0.6, 0.4, 0.4, and you explode this 1,000 times. Where is that page gone again? So sorry. You explode this 1,000 times, and you explode this 1,000 times, and you explode this 3 times only. Now, which is the best one? Action 1, 2, or 3? It is giving me 60%. It is giving me 40%.
Yes, action 1 is the best one.
So according to action 1 is the best one. What about action 3?
Action 3, we have explored only 3 times and we have got 0.4. So we cannot take the decision that this is the optimal.
So we know that action 1 is better than action 2, but action 3 we are uncertain. We don't know whether action 1 is best or whether action 3 is best. Can I say that? So this is the definition of greedy approach. So that is why we came up with the dithering concept. Here there is written dithering. Dithering, and one form of dithering is epsilon greedy. Epsilon greedy means like epsilon times I'll select the action. Like if I am given the epsilon thing as 0.1. 0.1 means 1 minus epsilon times I'll select the greedy action, and epsilon times I'll select the other actions uniformly at random, which you told me.
Okay.
Now, what is the limitation of, actually in the last classes of mine, I have also done this with the coding thing. Maybe I can show you, but you can also see in the YouTube video of my last lectures. I have also coded this. So limitation of epsilon greedy, what is this? Action 2 has no chance of, we are saying that either we'll go with the action 2, either we'll go with the action 3 with 1 minus epsilon probability, and with, epsilon probability, and with 1 minus epsilon, we'll go with the action 1. Am I correct? I know that action 2 is not the best one. Then why I'm exploring more action 2? I know that action 2 is not the best one. Because we got 40% here and we have explored 1,000 times. On the other hand, I know action 3 has to be explored more. But with epsilon probability, I am exploring action 2 and action 3. Both with like 0.1, I'm exploring both of them. So is it a right approach?
Yes, because when we are choosing some action, we always not thinking of the present payoff. We have to think of the future payoff as well. And the thing is that means at present maybe action 1 is the best one, but in respect of future payoff, maybe this action 2 will be better.
Yes. So so that's why epsilon greedy has also some limitations. That is why we came with softmax approach and Thompson sampling approach.
Okay.
So that these things, these topics I have covered in my previous lectures. You can go through that.
Okay.
And if you'll have any doubt, again, you can ask in the class. So let's continue where we have stopped. Any doubt till now?
No, so far it's all right.
Okay. So we were talking about the optimal value functions. What is the max expected return given st is equal to s? We talked about the value function and we are saying that what will be the maximum value function. And this pi star is equal to argmax of this value function. Now, this pi star means the optimal policy here. Argmax, what does it mean? Argmax doesn't return unique pi. There may be many optimal policy. Or I can say, there is not the optimal policy. There is a optimal policy, means there can be many optimal policies. If I am in a particular state, there can be various policy which can direct me to the particular action. I'll show you in the example, which I'll, maybe in that example we can't see. Oh, grid example. So I can, this is the target here. I have to reach here. So I can go here in the top. Here I can go right, top, right. What does it tell? It tells that there may be many optimal policy. I can go top also every time. I can go right also and reach to that particular state. You got this example?
Yes, I got it.
Okay. Now, what I told, there may be many optimal policy. There is not unique policy. If I talk about the value function, it is basically unique here. Whatever policy I'll follow, I'll go top, I'll go right, the value will always be the same with all those optimal policy which I'll obtain. Pi star may not be unique. But V star, if I talk about V star, it is unique for us. Optimal value function, let's go. I'll write the equation and then I'll explain you. Max should be here basically. I've explained you earlier about Q of S of A. You got this Q pi of S of A first of all. If I'm in the particular state and the action, what is the probability I'll go to the S dash? We have the action as well as we have the state when we are talking about the Q. When we are talking about V, we only have the state here. And then we are seeing in the whole trajectory that what will be the optimal actions here. Here, first action we know. then what is the expected reward, and then the future rewards. If I talk about the optimal value function, what I have done is same thing. If I have the state, I have the action. What is the probability I'll go to the S dash, given S and A. Then what is the expected reward? Now I'm given with the S, A and S dash plus gamma, discounted reward, plus max pi. Wait a second. Max is here, not here. Can you tell me how? Yes, any idea?
It tells us for means which policy it will give us the maximum discounted reward. Means the function will provide
Value, maximum value basically. Now we like here we don't have to keep it because we know the action. We know the policy, like we know what is the action, first action. Here we have to predict what is the policy, what is the optimal action to be performed here. First here is A is given to us. I'll take the action A and then behave optimally. Can I say that? I'll take first action, then I'll behave optimally. Am I correct with this line?
Yes.
Are you? Yes. Okay. V star of S is, I have here written, V pi of S is equal to summation over all the policies S given A. This I explained you what is it? Now, what I'm taking, if I'm talking about the optimal value here, I was talking about the V pi of S. If I'm talking about the optimal value, I am saying that over all A's, I'm talking what is the maximum A if I'm talking about Q star SA. In Q star, what is here? Or I'll expand this and then I'll tell you. Wait a second. Here I'm talking about it will optimally behave optimally from the current state, and in Q it will behave after taking a first action. So what is it? What is the difference between this equation and this equation? Let me keep it in the same frame. Yes. In Q star and the V star here, what is the difference? Yes. Come on. Same thing which I told you. In Q star S of A, Q star of SA, here I am saying what will be the max policy I'll follow. What will be the maximum policy I'll follow after taking this action. Here I'm first saying what is the maximum action it will perform. What for all of them, not for the here I'm not talking about the first one. I take action A, then behave optimally here. Here I'm taking behaving optimally from the current state. I can write pi star of S as if you have any doubt, you can interrupt me in between and I'll explain you again. Now, what is the policy here? What is the optimal policy here? Argmax A, summation of probability of S dash given SA into expected reward given SA S dash plus gamma V star of S dash. Only what I'm replacing is, if I'm taking the optimal value here, then I'll get the optimal policy over all A's. What this policy means, I get the all the maximum of act. Like basically, I'll get the optimal actions here when I'll perform this pi star of S. The maximum of what is the main motive? I'll get the maximum reward, maximum return here with this particular action here. So I can say it like this. Or I think let it be. Any doubt? Why I have written here max and why I have written here argmax? I have told you now only, like, what's the difference? Any idea? Or any doubt? Yes?
No, I could not follow because it was interrupted. So if you can repeat once again, it will be great.
Okay. Now, again, like Q star of SA, what does it mean? If I'll go again with this Q pi of SA, or I'll go from the starting and follow the flow here. V pi told me I have a given state and then what is the expected return? Q pi is telling me, what is Q telling me? I have the state, I have the action, then what is the expected return? Now, I told you about the Bellman equation of the V pi. What does V pi told me that? What is the probability? Like, what is the policy? I'll go to A. First of all, I have a given state. What is the policy will tell me what is the optimal, what is the action I'll perform. And then if I have S and A both, then what is the probability I'll land in S dash? Then what I'll get the expected reward. If I'll talk about this RT plus 1. RT plus 1, I can write it as like this. And this is the future reward. I explained you about that. And then what is Q pi? Q pi is, I'll not write this S and A because for the first reward, I'm telling RT plus 1. I know what is the first action here performed. So S, given S and A, then what is the probability of S dash? Now it was V pi and Q pi. Now I'm talking about the optimal value functions. Optimal value functions means when I'm talking about what is the maximum overall, maximum expected return by following the policy here. Then I told you about that if we talk about the policy, then there is not the optimal policy, there is a optimal policy. What does it mean? We don't have unique optimal policy. Like I showed you that grid, we can go up, we can go right. There are many ways we can reach to this by following the optimal policy. Like optimal actions, we can, like optimal policy will perform an action. We can perform multiple actions and then also we'll reach this max. So that is why we have written here argmax. Then I told you pi star may not be unique, but every pi will give me a unique value function, that is V star of S. Then coming to this optimal value function, now Q star of SA, the same thing which I have written here. The same thing I have written. Now, what is the, I'm talking about now max thing, max policy, because I'm talking about the max return. So, because I'm talking about the optimal value function. Now, what I'm saying is, the I'm given with S and A, then what is the probability I'll go to S dash, then what is the reward? I'm having S, A and S dash. Then I'll follow the max thing and then I'll go to the V pi. I'm doing max here because this action may or may not be optimal. This action has been performed in the first, I have taken the action and then behave it optimally. If I talk about the V star S, then I'm talking about, here I'm taking the max action for, like, max of action should be for all of them. It shouldn't be for the, like, first action shouldn't be performed like this. It should be for all, or it should perform optimally from all the states, starting from from the current state. It should perform optimally. This V star of S say me this. I should stop my video. This V star of S says me that I should perform optimally from the first state, first state only. Now pi star of S tells me argmax. Now pi star means what is the optimal policy. It is saying that the same thing. Like I should take the argmax of A. Just I have replaced this max with argmax here, because I am saying that I can have the multiple policies, multiple optimal policies. But if I'm talking about the value function, I'm saying that I can only have the unique value function. That is why I have written here max. You got it?
Yes, so for unique value function, I have the unique optimum value. That's why we are writing max. Otherwise, means we have the multiple. That's why we are writing argmax, right?
Yes, yes.
And I have another question to you. Means if you can please address that. That is a very basic question. Suppose we have a slotting machines. Means we have 7 armed. Okay, only 7 armed. Now, what I can do there, I can pull any of the arm. Means suppose third arm I am pulling repeatedly. Now means I little bit become confused sometimes here. Now pulling this arm, and I'm just pulling this arm and I'm getting some payoff. That's all. Now on third arm I am doing this. So I am in which means I am performing any action or not here.
You are performing action. Okay, this is the MAB thing. Multi-arm banded. Pulling the arm, pulling, these are the actions here. Okay. This is the full RL thing we are studying. You are saying, suppose I have ABC, I am pulling B. Correct? You are pulling
Right.
B. This here, B refers to the action here. Pulling action A, pulling action B, pulling action C. This is the MAB technique.
Yes.
Now
Okay.
we are talking about full RL. Here we are not having states. Here we are having the states in full RL. You got it?
Okay. Got it. So in this case, how will you calculate our value function?
Okay, I'll suggest you in the map thing, go to my previous lectures and then study about that. How the map will basically, how the map, techniques, greedy, epsilon greedy, Thompson sampling, how these work. I've also given the code, like I have also explained the code. Then in the next lecture, if you have any doubt, then we can extend that and we can study about that.
Okay, thank you. Actually, I missed few lectures. That's why this time. Okay, I'll check definitely. Thank you very much.
Okay. You got an overall idea about this map states action, what I told now?
Yes, absolutely clear.
Now, we have done what is the optimal queue, what is the am I audible? I think there's some
Yes. Now we are audible.
side. Sorry. Now I'll talk about some concepts of this norm, max norm, Cauchy sequence, Banach space, and all about the convergence. Let's go there. I'll try that we can cover the example, or I think value iteration will go to the proof afterwards. First, we'll cover the example, some questions I have brought for you. So what is finite MTP? If I talk about finite MTP, it means that my S is finite, states are finite, action are finite, and the expectation is bounded here. You know about norm? What is norm?
Means I know about L2 norm, L1 norm. That's
so like Euclidean norm, L2 norm, and all. So norm is basically the size of the vector space, or we can say about the distance or the size. We can say. Now I'm talking about the max norm here. I'm taking the v pi, the value function v pi, as the vector space. Wait a second. With S components here. And having max norm on the vector space. Max norm means supremum.
maximum size.
In the norm, we have three properties. It is basically non-negative. You can say norm of X is 0 if and only if X is equal to 0. Second is homogeneity. Just for the knowledge, I'm telling you, we'll use this triangle inequality in all our proofs. You know about triangle inequality? It is norm.
Yes, I know.
This is the triangle inequality. These are the norm, like three properties I have discussed. We can use in our proofs here. So that is why I have discussed. Triangle inequality will be used so much. So that is why. Now coming to complete. Okay, before going to complete normed vector space, let's go to the Cauchy sequence. Any idea what is it? Yes?
No, I don't.
Okay, it's fine. I'll write first the definition and then I'll explain. I'll explain like this maybe. what does it say is for every positive real epsilon greater than 0, I can find some point in the sequence beyond which if I pick any two elements, they are within epsilon of each other. Such a long definition. What it is saying is, if there is a sequence beyond a point, every point, if you'll pick any two elements, they'll be epsilon distance of each other. They'll be close to each other. What does it mean? Sequence in which elements are coming closer and closer to each other. That is basically a Cauchy sequence. Like 1 over example, 1 over n square, if you'll plug in the values, you will see that after in the sequence, they'll come, the points will come closer and closer. The distance between the points will be reduced after every point, basically. Sequence in like the elements in that sequence, the distance will reduce after every they'll become closer and closer. That is what the Cauchy sequence means. Or xn minus xn norm, it is less than epsilon. Means the same only, that the sequence in which elements are coming closer to each other after every passage of elements. You got it? Now, if every Cauchy sequence in the norm vector space, they converges to the point in the vector space, that is called complete normed vector space. You got, first of all, what is Cauchy sequence? When the elements are coming closer to each other, the distance between the elements are reducing. Got it?
Yes.
Now coming to complete normed vector space. This is also called as Banach space. What does complete normed vector space say? That if every Cauchy sequence in norm vector space converges to point in vector space, it is called as complete normed vector space. If every Cauchy sequence, the sequence which is coming, the elements in which are coming closer and closer to each other, if they converges basically to a limit, converges to a limit that is also in the space only, that is as complete normed vector space. You got it? Or I can say if every Cauchy sequence is convergent, then the vector space is complete.
Okay.
Now coming to this R pi of S reward I will get from the policy pi. We understood about the norm space. We understood what is the Cauchy sequence. We understood what is complete normed vector space. Now coming to R pi of S, reward I'll get by following the policy pi basically. Can you explain this, like the step by step I am explaining? If we have this S, then we'll go to A. Now, can you explain this R pi? Try at least to explain this equation.
R pi, that is reward under policy when we are starting from state S, and then that is equals to basically we are getting first we are taking one action when on a given state, and then we are just summing over A, and then we are means for the next state again we are means it takes us to the next state S1 means, and we are again summing up this thing.
Oh, sorry,
And
I have to write here P. Sorry. This is P here. Huh. Yes.
and then the expected value of the reward when this S means this previous state, this A and the next state is given. That means every time I need to means when I am reaching to the next state, that time I realize that the whether my previous state is was the right or wrong, or I need to do something else. So it's like this, isn't it?
Yes, it is giving me the expected reward. How? Yes, you are right. It tells me pi of A given S, that what is the policy I should follow if I start with S now for all like summing up over A. What is the policy? Like if I'll follow the policy, what will be the A given to me? Then now I am having S and A. What is the probability that I'll go to the S dash? And then now I'm having S, A, and S dash. What is the expected reward? Am I correct?
Yes, I mean that, yes. But you speak in more organized way. Means I means that word, that probability that should be mentioned.
Actually, I forgot to write it. It's fine. Probability, I start, what does it mean? Wait a second. Probability, I start with S and end with J. This is like first step transition probability under the policy pi. I start with S and I end with J. Like what is the probability that I'll start, that I'll end up in the state J when I take the action and according to the policy pi, basically. So what it is saying is, I'll take the policy says me that if I'm in the particular state, what will be the action taken? And then I'm having the state and action, then what is the probability of J? Nothing. It's just saying me what should be the, it will tell me what is the policy. Policy will tell me what is the action. If I'm in the state S, what action should be performed? And now I'm having the state and action. Then what is the probability I'll end up with the J? I'm starting with S, I'm ending with the J. What is the probability? How
Yes.
I'll calculate? I'll calculate what is the action. How I'll calculate the action? By the policy. When I'm having the state and action, then what is the probability of J? Now I'll write the two equations. Similar to this, there'll be a very less difference between them.
It is basically probability multiplication chain rule, right? Where what is your writing?
This one.
Means the previous one, probability multiplication chain
Yes,
rule, we have the
yes.
same thing like that.
Yes. This is suppose first equation, this equation, this is third, and this is fourth. I have modified the first equation to the third one and modified the second to fourth one. Can you tell me what I have done and what is the difference and what I'm assuming? What can be the assumption?
Just let me follow. Oh, this is means now that for the I think we have talked about the equation 2 already. So now for the third equations, the same means what we are doing that we are in state is means probability of being in next state is dash when we are in state is, and when we are taking policy pi, and then we are calculating the expected value of the reward. This is I think so.
I have changed this first to third. In first, there was this. It is not there. A was there. This is changed to pi s, and A
Okay.
was there, and this is changed to pi s.
Mhm.
How? I'll tell you. You were trying to explain the equation. It was correct. But now I'm trying to tell you what is the difference, how I came from 1 to 3 basically. I am assuming here the deterministic, I have many ways to go from S basically. I am assuming that there is a deterministic thing. Like if I am in A, there will be a one policy, one action. There'll be, it is deterministic. We are not having the stochastic thing. That is what I am assuming here. If I am assuming that this is deterministic, then I can write this pi A of S. Basically, I can write this as pi of S here. So I know this is deterministic. This will end up in this A only. That is why I'm not writing it. I'm writing this. And instead of pi like A, I'm writing this pi of S. I know that it will land to this A. Instead of this pi of A, I'm writing this pi of S. Similarly, I know that this will land. This is a deterministic thing. I'm not writing this. I'm writing only P of J given X and pi of, instead of A, I'm writing pi of S.
Yes, got it.
Now, R pi is S-dimensional vector here, and P pi here is S cross S dimensional stochastic matrix. Any idea what is stochastic matrix? Okay, I'll tell you. In stochastic matrix, it has a property. First, I'll tell you about the properties. The matrix whose rows add to 1 can write it like this. They all have to be basically non-negative elements. And lie between 0 and 1. This is basically the stochastic matrix, which I'm telling that P pi is a stochastic matrix. Now coming to V pi. Can you tell me by seeing this equation, what is it? I'll explain you, don't worry. Any
Gamma into what is this?
P
Rho.
pi. P
P.
pi.
Okay.
R pi means reward. This is one step transition function. Reward for one transition. This is the reward for one transition. This is the final cost. Basically, the V pi. It's okay. V pi only. It's confused, huh? This is the V pi, final cost or the terminal cost. And this is the probability, like P pi is where I'm going to land up, the probability of that, where I'm going to basically land up. And then this is the terminal cost. This is the reward basically. So V pi I'm saying is as the reward plus gamma into the probability of the terminal cost. And this is the terminal cost here. We'll also do the numericals now. Or I can write it as I'll take it common. This is basically V pi. This is also called as Green's equation. P pi is stochastic matrix, I told you. And here, this is basically invertible. How? How can we show that this is invertible? I can write I1. How can I show that this is invertible? I know that P pi is stochastic matrix.
Okay, so means this invertible means this is not a singular one, right?
Eigenvalues
So
of
everything is positive. Every element entry is positive, and it is lying between 0 or 1 only. So the determinant cannot be 0.
Yes, determinant cannot be 0. So can I say the eigenvalue, if we are not having 0, then determinant cannot be 0?
Yes, we can say that.
We can say that. Now, if I talk about this thing, wait a second. Stochastic, this P pi, I told you that the it is a stochastic matrix, and largest eigenvalue for the stochastic matrix is 1. I'll write the points here. Lies between largest eigenvalue of stochastic matrix 1. So P pi is like a largest can be 1 here. If I talk about gamma, it lies between 0 and 1. So basically gamma is basically less than 1 always. So if I multiply this with gamma here and P pi, it will be less than 1. Gamma into P pi. If P pi maximum is 1, gamma is less than 1, it will be less than 1 only. Multiplication. Then I minus gamma P pi. This is 1. This is less than 1. It cannot be 0. It cannot have eigenvalues 0. Eigenvalues here, sorry. Eigenvalues here of I is basically 1. 1. Identity matrix. It is less than 1. So eigenvalues cannot be 0, and this is a invertible. Can I say that?
Yes.
Cleared the got it clear, like whole picture what I told you, how it cannot be, like it is invertible. As long as eigenvalues are not 0, Determinant is not 0, it is invertible. Let's go forward.
So gamma is the means sort of hyperparameter, right here.
Think have you discounted reward? Have you heard about it?
Yes,
How?
discounted rate. Yes, I know.
This is the same. Yes, you can say that.
No, discounted reward is our mathematical term, RL term, but in
RL.
respect of programming, if we adjust gamma in respect of programming, can it be said hyperparameter?
Yes, yes, yes. You can say it. Yes. Now coming to next thing. We claim that VPile converge and okay. Let's start. I want that we should do with examples, but I think we'll stuck in this proofs and all. Okay. This is LPI is the Bellman operator here. It is the Bellman operator. What does it tell? I take V pi, apply L pi on it. It will give me again the V pi. So V pi is the fixed point of L pi. You got it? I take V pi. If I'll apply this L pi on it, it goes to some point. Again, I'll apply L pi on it. It goes to some point and then again and again. And then after some time, it will stay on the same point. That is called the fixed point. You got it?
Yes.
So V pi is the fixed point of L pi. Suppose you know about contraction mapping?
No, I don't.
Suppose U is a Banach space and it is a contraction mapping. What does it say? U has some function that is T of V and V has T of V, some function. And T of U and T of V will be closer to each other than U and V. U and V are closer to each other, but T of U and T of V will be closer to each other more than U and V were. This is basically called contraction mapping.
Got it.
Coming to Banach fixed point theorem. Suppose, first I'll write it and then explain. U is a Banach space. You know about Banach space? Yes?
No, I don't know. I have to study.
Wait a second, I'll tell you. I told you about complete normed vector space. I'll tell you again. We
No, I
have,
remember that.
you didn't got
Non-vector space. Hmm.
Banach spaces. First of all, I'll tell you what is Cauchy sequence. Cauchy sequence is if in the sequence the elements are coming closer and closer to each other, that is called as Cauchy sequence.
Mhm.
Got it?
Yeah, I remember that also. Yes.
The elements are coming close. Or next time I'll bring more examples to you for you so that you can understand this Banach space. I'll come up with the examples. So this is the Cauchy sequence, and if the Cauchy sequence is converging to a point, if every
Which
Cauchy,
is in the vector space itself, then it is.
then it is complete normed vector space,
Hmm.
or you can say Banach fixed point or Banach space. Sorry.
Okay.
Got it?
Mhm.
I'll come up with examples next time. So, contraction mapping, you got it? That
Yes, I understood.
Have you studied about fixed point earlier also? Or no? Like
No,
earlier?
I have. This is the first time I just got exposure.
Okay. Fixed point is I'm applying again and again. Like if I'll tell you about L pi of V, I'm applying L pi on it again and again. I'll go to some point, then I'll go to some point, then again I'll go to some point, and then I'll stay on that point only. That is basically the fixed point. Like there exists a unique V star in V such that TV star is equal to V star. If I'll apply T has a fixed point. If I apply T on V star, I'll go on applying it and then I'll converge to and then it will remain the same after some time. You can also see these examples of the fixed point being used in the computer networks as well. Maybe for arbitrary V naught in U, the sequence Vn defined by Vn plus 1, V power n plus 1 is equal to T into V power n is equal to T power n plus 1 into V naught. Basically, it says that this is the fixed point. It will converge to V star basically. What does it mean? If I have V1 goes to T V naught, V2 goes to TV1, and at the end V star we'll get. Or I'll talk about this. What's happening here? Can you see my screen?
Yes, I can.
What I'm saying is, if I have V1 applying T into V0, if I have V0 applying T into V0, I'm going to V1. Then applying T into V1, I'm going to V2. And at the end, we'll go to the V star here. So here, I have two actions I'm assuming. Action 1 and action 2. Action 2, if I'm in state 1, I'll perform action 2. I'll be in the state 1 only with the reward -1. Usually we can say as the negative reward as cost also. If I'm in the 1, I'll perform action 1. I'll go to 2 with the reward 1. If I'm in 2, perform action 1, go to 1 with the reward 1, and action 2, reward 1. So if I'll talk about the policy, over the reward 1, if I'll talk about if I'm taking the action 1 in the state 1 and action 2 in the state 2, R pi plus gamma V pi, P pi into V pi. So here I'm saying that if I'm performing the action 1, I have the reward 1 plus gamma into V pi, I'm landing in 2. If I'm in the 2, I'm talking about the action 1. I'm landing in 1. You got this? Or I'll
Yes.
Now, I can get this as, I can substitute the value here of V pi of 2 here. So I'm doing nothing. I'm just calculating what is this V pi of 1. I'm substituting this V pi of 2 here. And then 1 plus gamma, here 1 plus gamma V pi of 1, 1 plus gamma, gamma square V pi of 1. I shifted it to left hand side, 1 plus gamma. So V pi of 1 is 1 plus gamma over 1 minus gamma square, or I can write it as which is equal to 1 over 1 minus gamma. Similarly, if we'll solve for V pi of 2, we'll get it as 1 over 1 minus gamma here. Now, if I'll perform the action 2 here, Policy says me, if you are in the state 1, you have to perform action 2. Policy says me, if I am in action 2, I have to perform action 1. Similarly, I don't know why these lines are coming. -1 is the reward this time. So I have written here -1. Got this? These two equations?
Yes.
Are you confused by so many terminologies and the concepts which I have given you, or like you are crystal clear?
No, actually, means the numericals equations are so many. So just when we are substituting something, the first time it seems to be confused, but later on when I will see, then it will be fine, no issue.
Yes, yes. So just substituting again, v pi of 2 -1 plus gamma v pi of 1 here. So v pi of 1 is equal to -1 minus gamma plus gamma square v pi of 1. Taking it to left hand side. So here we'll get it -1 over -1 minus gamma. Basically, this we'll get it. If we'll plot it, we'll get here 1 over 1 minus gamma. -1 over -1 minus gamma. -1 over, okay, it will be like this. Okay, leave this. This is basically, we'll get from this. This is the Banach fixed point theorem, which I'm just telling you how it proceeds. Or I can give you the fixed, how, like, what is the fixed point with the intuition of computer network. I think it in CSMA, to calculate, if we talk about in the computer networks, in CSMA, it's used for the collision probability or the number of transmissions. In that concept also, we are fine when we are doing that CSMA thing. In that also, we are using this fixed point thing only. Maybe I'll go more, like that will be more deep concept. Okay, leave that. Again, coming to the contraction mapping only, I'll explain you in more detail, like mathematically only. What I told you, that if we have u and v and a function tu and tv, t of u and t of v, t of u and t of v will be closer to each other than u and v were. Am I correct? This was what is the contraction mapping. T is a contraction if TU minus TV, don't know why these lines are coming up. TU minus TV is less than lambda of U minus V. Can you tell me what is it? Explained you now only. Yes.
This contraction mapping.
Huh. I have U and V. They are some distance apart. If I'll apply T on both of them, they'll be closer than what they were before. This is what is contraction mapping. Now I'll use it to prove that our Vn is basically the value function which we are doing is that is Cauchy nature. So I'll prove the L pi is the contraction here, and then contraction, for that the Cauchy thing. Okay. What is the triangular mapping here? Can you tell me? Simple Vn plus 1 norm minus Vn norm. Am I correct?
Yes.
Can I write it like this? I haven't done any triangular inequality thing. I have written this. Just added n plus m by 2 and subtracted n plus m by 2. Yes, we can do now.
Yes, we can do.
Yes. Now applying triangular inequality. Is it correct?
Yes, correct.
So what we are saying, we are supposing that there are 3 points. Vn is a point in a space. Vn plus 1 m is another point in the space. And Vn plus m by 2 is the third point. We can also do like this. Okay, for the summation, I think. Same thing I have written like this. Vn plus inequality. Vn plus m minus Vn plus m minus 1 plus Vn plus m minus 1 minus Vn. Or you can split it again. Vn plus m minus Vn plus m minus 1 plus Vn plus m minus 1 minus Vn plus m minus 2 plus Vn plus m minus 2 minus Vn, so on. No, like this only. Or, wait a second, let me write, I'll explain you. what I have done is I have just written this Vn plus m minus Vn plus m minus 1. The same thing. Vn plus m minus 1, just added this and subtracted this and added this. Then I have applied triangular inequality. This is the same here. I have split this again to this Vn plus m minus 1 minus Vn plus m minus 2. And again, this plus and minus. This we can do it again and again. And this will be the last term, Vn plus 1 minus Vn. Got it?
Yes, got it.
Now I can write it as how I have written this. The summation of k is equal to m minus 1. Summation, if I'll talk about this, wait a second. Summation of k is equal to 0. I'm taking this as 0, 0 to
m minus 1. That
m minus n plus k plus 1. M is equal to basically k plus 1 I'm taking. If m is equal to k plus 1, I can say that it is going to k is equal to m minus 1. You got this thing? If I'm saying that m is equal to k plus 1, I'm just taking this m minus 1 here. And this is minus Vn, no? Vn plus k, where it is 0 here.
Yes.
This is how, actually this was, this expression was given in the, like directly from this to this was given in the lecture. So it took me time how we came to this basically. This is how, I'll tell you. Vn plus 1, sorry, Vn plus 1 minus Vn is less than, we can write this. What I'm saying is we can write this Vn plus m minus Vn is less than convinced?
Convinced.
Now, here we have written about the definition of this fixed point. T of Vn, Vn plus 1 is equal to T of n plus 1 into V naught. So here we can write this Vn plus k as T of n plus k into V1 minus T of n plus k into V naught by the definition above.
Contraction mapping.
Now contraction mapping. Now I think you have started relating the dots. It is less than this thing. Basically, this sum is equal to lambda n 1 minus lambda power m 1 minus lambda v1 minus v0. So as n and m becomes large, it becomes smaller and smaller, the contraction thing. So sequence of Vn is Cauchy. You got how I have proved this sequence?
I have only one question. Means in last line, you have written lambda n into 1 minus lambda m, right? and divided by 1 minus lambda means we have the lambda to the power n plus k. So from that was m minus 1. Then we are putting.
Okay, wait a second. Okay, I'll explain this in the next lecture. How from the submission I'm going to this. I have also not noted this. Okay, this sum is how going to this point. I'll explain you in the next lecture.
Okay.
And then I'll explain the convergence proof overall, and I'll the things which I have told you about the contraction mapping, about the Banach fixed point theory, Banach space. I'll basically join all the dots between them. Like how this is what we are trying to prove here, what is the convergence proof. Then we'll go to the value iteration proof. Then we'll go
Okay, I got it. You have multiplied 1 minus lambda by means denominator and numerator, and we are getting this thing because.
Okay. Yes. Wait a
Got
second.
it. Got it. Got it. Okay. Thank you.
Okay. Let me figure out. Okay. 1 minus lambda. Okay. I think 10 minutes are left. I shouldn't move forward, but what can I do is I can give you a question which we can solve in the next lecture. I'll expect you to solve this question. It's an easy question only, and come up with the solution in the next lecture.
Okay. Actually, today is my first class. I could not attend your previous class, none of the class. Today is my first class. That's why, means,
It's fine. You can see the video lectures, the YouTube video, and you can also, I'll write in the chat. You can see professor's lectures as well, and I have written in the chat the channel name.
Okay.
I'll provide you with the email ID if you have any doubts.
Yes, please.
That I should cover in the next lecture. If you have any doubt in the assignment, I cannot solve the assignment question as such, but I'll come up with the question which is related to the assignment, so that you can solve the particular question.
Okay.
So, but for that, you should mail me beforehand only, so that I'll in the next class I should prepare with that things.
Okay.
That topics. Okay. And I'll give you the question. Just try to solve it. If not, then we'll solve it in the next class.
Okay.
This is MTP question only. A machine can be in working or non-working state if working, or if we have time, I think we can solve now. Operating the machine cost incurs zero cost, and on other hand, operating a non-working machine with one time period incurs cost of 3 units. If machine is replaced by a new machine with cost of 6 units, it stays working for one time epoch. think the question is long enough. Working machine can transition to non-working with probability 0.3. System needs to be operated for 4 total time epochs with an objective of minimizing the cost, formulate MDP, and provide optimal policy. Question is long enough. So what is the question? A machine can be working or non-working state. So what is the state here?
Working or non-working. 2 states.
2 states. Now, if working, the operating machine incurs 0 cost. On the other hand, operating a non-working machine with 1 time period, it incurs 3 units. So if it is non-working, it will incur the cost of 3 units. If the machine is replaced by the new machine, it will have the 6 units of cost. Working machine can be transitioned to non-working with the probability of 0.3. I can say working to working is 0.7 probability and working to non-working is 0.3. If system needs to be now for total 4 time epochs, I have to calculate with an objective of minimizing. The main motive is to, like, we are dealing with maximizing the reward. Here I'm saying minimize that reward, minimize that negative reward, or minimize the cost, formulate the MDP, and provide optimal policy. So just try it. If you like, we'll discuss in the next class. Just try to do this question.
Okay. And one more question, just if you don't mind, means your recorded lectures, means can you give me the link of the recorded lectures?
I showed you this channel, YouTube channel. Here you can install the recorded lectures.
Okay. Thanks.
And you can come up with the mail me like earlier only, before the lecture, like 3-4 days earlier only, like these are the doubts, so that I can cover in the next lecture.
Okay, thank you.
Examples I can bring with more examples also.
Okay, thanks a lot.
Okay, thank you. Let me stop the recording.